Part A1. Draw the standing wave pattern of the fundamental mode and first two overtones produced by a vibrating stretch string in three separate diagrams. Mark nodes as N and antinodes as A diagram. In the diagram, neglect the incorrection. A part 1. We have to draw three diagrams. First one, fundamental. At the fundamental, there is only one loop. This point is a node and this point is an antinode. Again this point node. Fundamental. Then at the first overtone, there are two loops. Node, antinode. Then in the second overtone, there are three loops. We have to mark node and antinode. Antinode means points with the maximum displacement. At the node, displacement is 0. Then part 2, obtain an expression for the frequency Fn in the nth harmonic in terms of N, T, L and M, which where T is the tension, L is the length and M is the mass per unit length of the string. Nth harmonic. This is the fundamental. At the fundamental, there is only one loop. And we can get this one is the first harmonic. This is the second overtone. At the second overtone, there are two loops. It is the second harmonic. So this one is the first overtone. It is the second harmonic. I will write overtone number and harmonic number. Overtone, harmonic. We have to identify nth harmonic. This one is the fundamental and this one is the first overtone, second overtone. Then considering harmonic number, this one is the first harmonic, second harmonic, third harmonic. Now we have to write the frequency Fn. It means frequency of nth harmonic. When considering first harmony, there is only one loop. For the second harmony, there are two loops. Third harmony, there are three loops. Then we can get for the nth harmony, there are n loops. We know that length of a loop is wavelength divided by 2. Length of one loop, lambda divided by 2. Then there are n loops. Then total length is lambda divided by 2 into n. Should be equals to length of the wire. Then we can subject lambda 2L over n. Lambda value is 2L over n. Now we have to write the relationship for frequency. Then we can use V equals F lambda. V equals F lambda. Velocity of wave in the string is given as T of M root. T is the tension, M is mass per unit length. Mass per unit length means mass of a 1 meter length of wire equals to frequency is Fn. We can substitute lambda value 2L over N. 2L over N. Then we have subject Fn. Fn equals, we can bring this term to the left hand side as the reciprocal. N divided by 2L into root T over N. It is the frequency for nth harmony. Then part 3, for a given string, state two possible ways to change the harmonic frequency. We have to write two possible ways to change the harmonic frequency. When considering this equation, we can get a different harmonic frequency by changing tension. They have given a string, therefore we can't change simple m value, it is constant for the given string. Therefore, we can change L value, length of the string. Then we can write answer for part 3 by changing length and by changing tension. Then part B, a harp like a musical instrument shown in figure 1 consists of 7 identical stretched strings with different lengths. The longest string of length L1 produces the musical note C with the fundamental frequency 260 Hz. The corresponding length of the string which produce all the musical notes are given in the table as function of L. L1 they have given with frequency with L over L naught, L over L1 value. Part 1, if all strings are under the same tension, calculate the fundamental frequencies of musical notes F and M. We have to calculate frequency for F and M. We can get that according to this relationship. Fundamental frequency is inversely proportional to length. F is inversely proportional to length. Therefore, we can write B part 1. Fundamental frequency is inversely proportional to length. Then we can consider fundamental frequency for C note 260 inversely proportional to, they have given that L over L naught value, L over L1 value. It means corresponding length divided by length of chord when getting 260 frequency, it is L1. Then we can get 260 inversely proportional to L1. First equation. Now we have to calculate fundamental frequencies of F and B. Then I will consider F fundamental frequency. I will get fundamental frequency as F2 inversely proportional to 1 over length of the fundamental length of the wire, then we can consider that they have given for the S naught, L of L1 value is 0.7. Then L of L1 value is 0.7. Then L value is 0.7 L1. Then we can substitute 0.7 L1. It is the second equation. Then we can divide the equations to get the F2 frequency. F2 means frequency of F, not F. Musical note F. Then I will divide first equation and second equation. No, second equation and first equation. F2 divided by 260 equals to 0.7 L1 divided by 1 over L1. You can cancel out L1. Then F2 is 260 divided by 0.7. 2600 divided by 7. Then we can divide it. 26 divided by 7, 3, 21, 5 remaining. 50 divided by 7, 7. 1 remaining. 10 divided by 7, 1. 3 remaining. 30 divided by 7, 4 hertz. 371.4 hertz. We can get it approximately 371 hertz. Then we have to calculate the frequency for node B. In considering node B, they have given that L of L1 value is 0.53. And we can use same method to get the frequency. I will write F3 as the node frequency of node B. F3 is inversely proportional to 1 over corresponding length, corresponding resonance length is 0.53 L1. They have given that L divided by L1 0.53 for the node B. Then L1 is, L is 0.53 L1. This is the corresponding resonance length for node B. Then we can substitute 0.53 L1. It is the third equation. Now again we can divide third equation and first equation to get the frequency. I will divide it. Third equation divided by first equation. F3 divided by 260 equals 0.53 L1 divided by 0.7, 1 over 0.7 L1. Then we have to multiply by reciprocal. Now we can calculate F3, 1 over L1. We have divided first equation and third equation. Then we can get 260 divided by 0.53, 2600 divided by, 26,000 divided by 53. Then we can get the answer 490.5. Frequency is 490.5 Hertz. Now part 2. To obtain a correct musical note, the frequency can be tuned by adjusting tension of the string. By what percentage should the tension of the string adjust to change the frequency by 1%? We can get again the relationship we have obtained to nth harmonic. I will write it again. Fn equals to n over 2L square root of tension over m. When considering fundamentals, we know that there is only one loop, then n value is 1. Frequency directly proportional to square root of tension. Now we are trying to change tension. Then we can write frequency directly proportional to square root of tension. Now we have to get a change of 1%, frequency change of 1%. I will consider initial initial tension is T. Then the tension is T, frequency F. Now we have to change 1%. We have to change frequency by 1%. Then new frequency should be 101 F over 100. We have given that the change of frequency should be 1%. I have considered 1% frequency increasement. 1% increasement means if the initial frequency is F, final frequency should be 101 F over 100. Then I will consider new tension as T dash. Now there are two equations. I will divide equations. We can cancel out F. We can bring 100 to numerator. 100 over 101 equals to tension over new tension square root. Now we have to get the percentage change of tension. I will get the square of equation 100 squared divided by 101 squared T over T dash. Then we can subject new tension T dash. T dash equals T times 101 squared divided by 100 squared. T dash equals T times 101 divided by 100, 1.01 square. One into 101, 1 into 1, 1 into 0, 0, 1 into 1, 1, 0, 0, 0, 1, 0, 2, 0, 1. We have to separate two decimal places. T dash equals 102.01 T. Sorry, we have to separate four decimal places. In 1.0201 T. I will get it as 1.02, approximately equals to 1.02 T. Then percentage change of tension, it means change of tension divided by initial change into 100. Change of tension is, we can subtract 1.02 T and T. 1.02 T minus T divided by initial value T, we have to multiply by 100%. Then 0.02 T divided by T times 100. We can cancel out T term 2%. Then percentage change of tension is 2%. Part C, a student designs and builds a set of sandpipes to produce musical notes given in the above table by using narrow PVC pipes with different lengths as shown in the figure. Lower end of the pipes are closed with corks. Part A, Part 1. Draw the standing wave pattern of the fundamental mode and the first two overtones produced by one end closed pipe with pipe of length L in three separate diagrams. Mark notes as N and antinodes as A in the diagram. Neglect incorrection. Then we can consider it is a closed pipe. See part 1. Closed pipe. We know that at the closed end it should have a antinode. Node. It should have a node. Then fundamental wave pattern is this one. Node, antinode. Length is L. You have to mark it. It is given as L. This one is the fundamental. For the first overtone, you have to get same length and we have to draw the corresponding overtone. First overtone is this one. There is only one loop and half of a loop. Antinode, node, again antinode, node. Then we have to draw the second overtone. At the second overtone, there are two full loops. Then node, 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 antinode, antinode, antinode. Part 2. Calculate the required length of pipe in centimeters which produces musical note C and B. Assume that velocity of sound in air at room temperature is 340 meters per second. When producing note C, it should be a wave pattern like this, fundamental. For the fundamental frequency, lambda over 4, 1/4 of wavelength, equals 12. Then we can get lambda over 4 equals L. Lambda equals 4L. Then we can use V equals S lambda. They have given that velocity of sound 340. Fundamental frequency 260. Multiply by, we can substitute wavelength by using this equation 4L. Then we have to simplify it. We can cancel out 0, divide by 2, 2, divide by 2, 17, 17 divide by 2 times 26, 52. 17 divided by 52. I will divide it. 0, 170 divided by 52, 3, 3 into 2, 6, 3 into 5, 15, 10 minus 6, 4, 6 minus 5, 1, 0, 140 divided by 52, 2, 0.32, 2 2 into 2, 6, 4, 2 into 5, 10, 10 minus 4, 6, 3 minus 0, 3, then 360 divided by 52, 7, 7 into 2, 14, 1 remaining, 7 into 5, 35 plus 1, 7 into 2, 14, 1 remaining, 7 into 5, 35 plus 1, 36, 364. No, then we have to get 6. Now, length should be 0.326 meters. We can write it 0.32 centimeters. Sorry, 32 centimeters. 32.6 centimeters. When considering next decimal place, 32.69 is the answer. Therefore, you can write 32.6 so correctly rounded off value 32.7 centimeters. Then we have to find the corresponding length for node B. Now we can use same relationship. We know that frequency is inversely proportional to length when considering B. Frequency of B is, we have found it 490.5. We can get it frequency 490.57. We have found it in part B. We have to calculate the corresponding length. I will consider length as L. We can use rounded off whole number 491 when calculating length. And we can consider this one as the first equation. For the node C, frequency is 260. It should be directly proportional to 1 over corresponding length 0.326 meters. It is the second equation. Now we can divide both the equations. 490 divided by 260 equals to L divided by 0.326. Then we can find the L value. 0.326 multiplied by 26 over 49. By simplifying, we can get the answer 17.31 centimeters. It means 0.173 meters or 17.3 centimeters. In part 3, the longest pipe is found to be produce the frequency of 255 Hz instead of 260. By what distance should the cork be moved to obtain the frequency 260 Hz? Now we have to calculate the change of length. They have given that when producing 255 Hertz frequency, length is the value obtained in part 1. When producing 255, we have to use the length obtained in part 1, so part 2 for node C. It means 32.6 centimeters. 32.6, so we can get 0.326 meters. Then we know that frequency is inversely proportional to length. Now we have calculated 0.326 length for 260 Hz. What they have given, it is not 250. It is 255. Directly proportional to 1 over length 0.326. I will consider this equation as A. Now we have to calculate length for 260. We have to find the L value. Then we can divide equation A and B. 255 divided by 260 should be equal to 0.326 L over 0.326. Then we can simplify and we can get the L value 33.3 centimeters. Therefore, the initial corresponding length length to frequency 255 is 0.326 meters. We can write this one 0.333 meters. Corresponding length for 260 hertz 0.333. Therefore, change of length. We have to calculate change of length. We can subtract 0.333 minus 0.326. 13 minus 6, 9. Sorry, 13 minus 6, 7. 2 minus 2, 0. 0.007 meters, approximately 0.7 centimeters. Then part 4, if the cork fell completely out of pipe, what would happen to the fundamental frequency produced by the pipe? Justify answer with the suitable diagram. Cork has been removed. Therefore, we can consider it as an open pipe, like this. Now we know that length is equals to lambda divided by 2, not 4. It means new wavelength is 2 times L. Length equals lambda divided by 2, lambda equals length into 2, 2L. Then lambda becomes 2 times. According to V equals S lambda, V is constant. Now, lambda becomes half. For the initial situation, we can take the answer when getting this wave pattern. Lambda over 4 equals L. Now, lambda equals 4L. Then, according to this diagram, lambda equals 2L. Lambda becomes half of initial wavelength. Velocity is constant. Velocity of air, velocity of sound wave in air is a constant. When lambda becomes half, frequency should be 2 times. Therefore, we can write, therefore, frequency should be doubled.